Hi, welcome to Mathematics with Tom. This is Tom. I am Tom. And today we're going to look at solving this first order linear differential equation. We have y prime equals ay plus q. And just for clarity, we could also write this as dy dt. So this way we know that this is y is a function of t equals a, and remember y is a function of t, so y of t, and q is some input or source function, we'll call it, and this is a function of t, but it has nothing to do with the y's, but it does affect our solution. So what we're going to do is we're going to solve this problem. Now, I'm going to use this first bit of notation. When we solve it, our first idea is let's isolate the y's. So let's do this. Isolate y. That's not y prime, that's just y's, plural. So if I do this, I have y prime minus ay equals q. Now, at this point, what we have really is we have a time to think. And here's what I'd like you to notice. Notice that this left-hand side, this is where we need to be, we really need to be creative. It looks similar. It looks similar to the result of a product rule. A product rule. I mean, imagine this. Imagine that if I had some function m, so let m be a function. Oops, I'm going to use capital M. So let m be a function. Be a function of t. So consider this. If I was to take the function m times the function y, this is, or you could use f's and g, like maybe in calculus, and I want to take their derivative. Well, it's going to be the first. It's going to be an m times y prime plus, and I'm going to write them in this order, then it's going to be the derivative of the first times the second. Well, wow, that sure is close to what we have above. Look at what we have above. We have a y prime. We have a minus, I'm going to write it plus, we have a negative a times y. Well, m can't be y, oops, it's an m prime. A can't be m, but I wonder if it can be something similar. So the question then is there some function m, or what is a function m, that I can multiply the left side, and we'll worry about the right side, so that I can rewrite the left side into using this product rule. So here's what we're going to do. So we want to find this function, find this function m. And here's what we're going to do. So this is what we want. So we want m times y prime, so that it's going to equal if I multiply the left side of my differential equation. So m times y prime minus ay. All right, well, we know the derivative of the left side because we just calculated that down here. So I'll just rewrite that. So I have m y prime plus m prime y. And now let's distribute the m y prime minus a m y. All right. I think, yeah, let's see. Oh, notice this. Look, we've got a little bit of cleanup we can do. On both sides of the equation, I have an my prime. My prime. So those will reduce. And then if we take a look at what we have now I have this. I have an m prime y equals minus a m y. Now, notice, oh, here, this is better than we could have asked for, because notice you always have to be careful when you divide by y. But if y was 0, this whole equation, if we looked back over to where we'd started, this wouldn't even be an interesting problem. This would have just been the problem that some function q of t equals 0. So that wouldn't even be a differential equation. So we can say that y is not the 0 function. All right, well, if that's the case, I can divide both sides by y, and I have m prime equals minus a times y. Oops, not ay, a m. Wait a minute. We've actually seen this, not with an m prime and an m, but with a y prime. We've seen this. We've seen y prime equals. We've seen ay, ay. We've seen that. If I put a minus sign, that's not going to change what we've seen before. In other words, the solution to this is that m has to equal e to the minus a t. That's the function m, and that function m is called an integrating factor. Integrating factor. In some texts, you'll see it with the Greek character of mu, but I like big capital M. It's easy to see. It doesn't get lost in all the details and careful work that we're going to have to be doing. This is our integrating factor. Let's see how we can use it. So now we can solve. Solve y prime minus ay equals q by multiplying by, I should say, be even more specific, multiplying both sides by m. All right, here we go. Let's do just that. We're going to do that on the next screen. Here we go. Here's my new screen. So when I do this, I'm going to have m. I'm going to start with my prime minus m a y equals m times q. And now let's go ahead and let's plug in. Well, actually, before we do this, this left side, this we know by design. This we know is m times y. This is the derivative with respect to t of m times y. That we know for sure. Equals m times q. Now let's go back and replace m. So I have on the left side, I have the derivative with respect to t of e to the minus a t times y equals e to the minus a t times q. And remember, q is a function of t. Now, now we've got all the y's on one side, and we have a derivative, the integral of a derivative. We know that because we've learned the fundamental theorem of calculus. So here's what we're going to do. Our limits, we're going to integrate both sides, and we're going to use this. Our limits of integration, are, so we normally, a differential equation models some kind of observation from, and when our observation starts, we usually call that time 0. There are other times when you could start at 1 or times 2, but usually we start at time 0. So limits of integration are, we're going to start when y of 0, and then we want to model this out into infinite time. So limits of integration are from time is 0, so that means y of 0, and out to some function y of t. Okay, so let's take the integral. Let's apply this to the function above. So I'm going to take the integral from y of 0 to y of t, derivative with respect to t of e to the minus a t times y dt equals, now we're going to take the integral. Now in this case, we're just dealing with t's. There's no functions of y, so we'll just use the t part. So from 0 to t. And now instead of the t's, just for clarity, we're going to use s. So we're going to write this as e to the minus a s q of s ds. All the s's are as a dummy variable so that when you substitute, you don't get your t confused with a t that's already there. So that way the s gets substituted with a t. It's just a clarity thing. Okay, but if you use t's, you're going to get the same result as long as you don't get confused. Now, let's take this. We know the integral of the derivative is just the function evaluated at its limits. So this becomes e to the minus a t y of t minus, now this is the next one is going to be e to the minus a, well here t is 0 and this is y of 0 equals, and then the right hand side doesn't change, it's still from 0 to t, e to the minus a s q of s ds. Okay, let's now notice e to the 0, this is just going to be a 1. So when I rewrite this, I have e to the minus a t y of t, and this is going to become minus y of 0 equals the integral 0 to t e minus a s q of s ds. Okay, but now let's add the y of 0. So I have e to the minus a t y of t. Remember, that's what we're solving for, is we're trying to figure out what in the world y is. So y of t, this equals y of 0 plus this integral here is from 0 to t e to the minus a s q of s ds. Okay. Oh, I think we're making progress. Notice this. E to the minus at. A lot of us get this a little bit. We may not be comfortable with this at first. But this is, so we're going to do a little bit of scratch work here. I'm going to do it in light blue just so we can see this. E to the minus at is the same as 1 over e to the positive at. So if I was to multiply by the reciprocal, well, the reciprocal of e to the at, so the reciprocal, this is 1 over, the reciprocal of 1 over e to the at is simply e to the at. So I'm going to multiply every term here by e to the at. So I'll write this so you can see this. E to the at, all you have to do is just change the minus sign on these. That works out so nicely, times e to the minus a ty of t equals e to the a ty of 0, oops, should have done that in white, y 0 plus e to the at times the integral from 0 to t of e to the minus a s q of s ds. And we're almost done. We simplify this. We have y of t equals e to the at times y of 0 plus e to the at, the integral from 0 to t of e to the minus a s q of s ds. There is our solution. We're all done. We now know all of differential equations. Well, no, not exactly. But look at what we've got here. This piece right here, this is e to the at. We've already seen that. And y of 0, that's just some number. It could be 1. It could be 5. Square root of 2. Wait a minute. This is going to, we've already seen, this is going to be some part of our null solution. And we know that that's going to work. In earlier videos, we called the y of 0 just some c, but now we know that y of 0, that c is really dependent on the initial condition, the starting point of this equation. And then this, the rest of this, is going to give me a bit of it. It'll be y particular plus some other c1 y null. And obviously the y nulls will then be combined. So that is how we solve this differential equation for all cases. So in the few upcoming videos, what we're going to do now is we're going to study what happens for different input functions, what happens for different functions for q. I hope that helps. Thanks for watching.